the last of the four conic sections is called the hyperbola. And we've actually seen hyperbolas before in this course. You might remember back in the first semester, we did things like y equals 1 over x. And when we graphed y equals 1 over x, it looked like this. Here I have it phrased as xy equals 1, but it could also be y equals 1 over x. Remember the rational functions unit? So hyperbolas have this property that there are these two asymptotes that cross each other. And then you have these two branches that look like sort of rotated parabola looking things. And those two branches are the two branches of a single hyperbola. So this isn't two hyperbolas, it's one hyperbola that has two branches. Now, and the reason that works is if I rewrite this as like xy equals 1, the bigger x gets, the smaller y needs to get, so that the product always stays equal to 1. 1, 1 is actually a point. 1, 1 is actually a point. And then it gets closer and closer to the x-axis, making that asymptote. On the other hand, if the x value is some kind of fraction, then you need a bigger y value in order to make the product still equal to 1, and that's where we get our vertical asymptote for. But since negative times negative is positive also, we end up with a second branch. So that's the type of hyperbola that we've already seen, f of x equals something like 1 over x. But in this unit, we're going to see another sort of different looking equation that also produces a hyperbola. And to do this, I want to compare the graph or the equation of a circle. So x squared plus y squared equals 1. Of course, that has 1, 0, 0, 1, negative 1, 0, 0, negative 1. But it's like there's not any large numbers, because if you have any number for x or y being bigger than 1, you can't square it and add on something else that's at most 0 and get 1 still. So x squared plus y squared equals 1 is a sort of limited curve that's in a small region of the plane. If I come over to Desmos here, and I go here, and I type in x squared plus y squared equals 1, and I zoom in on that. Now, what would happen if I were to change this plus sign into a minus sign? So I have this, and the question is, what about x squared minus y squared equals 1? What do you think that looks like? See what happens. Take this plus key, delete it. Makes a weird thing for a second as it's x squared times y squared equals 1. But then I put in the minus sign and check it out. Just like this. And just to show you what this is a bit more, if I draw in the line y equals x and y equals negative x, and I make those into dotted lines, I hope you can see, if you turn your head to the right 45 degrees, that this looks a lot like the hyperbola that we've seen already, but a hyperbola that is symmetric with respect to the x-axis instead of with respect to, remember, our original hyperbola was symmetric. Actually, I still have the line in there, symmetric to the line y equals to this y equals negative x, it's symmetrical with respect to that. Whereas this one is symmetric. It has different asymptotes. The first one had asymptotes at the x-axis, y-axis. This kind doesn't have vertical and horizontal asymptotes. It has these slanted asymptotes. And we're going to learn more about equations of this form, x squared minus y squared equals 1, and variations on it. So I just want to say a little more about x squared minus y squared equals 1 and why this kind of happens. One thing that we could realize is that if you were to put 0 in for x, if you put 1 in for x, y would have to be 0. So this curve has the point 1, 0 on it. But if we put something bigger in, like 2, x squared minus y squared equals 1 means that x squared and y squared are fairly close to each other. Like they're almost the same value. They're just off by 1. So x squared, so 2 squared is 4. So we'd have to do 2 square root of 3 would be that point. I think I need a bigger axis here. So x squared minus y squared equals 1. One point is 1, 0. Another point is 2 comma square root of 3. Square root of 3 is like 1.7. Another point is 3 comma square root of 8, because 3 squared is 9, square root of 8 squared is 8. 9 minus 8 is 1. So for sure, the y coordinate is less than the x coordinate. However, it's getting closer to it. So 4 square root of 15, because 16 minus 15 is 1. But basically, we end up with the point 4 and slightly less than 4. And that's why, at least for this sort of branch that I have, kind of goes like that. It gets closer and closer to the line y equals x. But it never actually gets there, because in order to be y equals x, x squared and y squared would have to be the same number, and then the difference wouldn't be 1 anymore, it would be 0. But if I were to say like 10, I'd have to put square root of 99 there, which is extremely close to 10. And that's why we have that branch. Well, if the y was negative, that would work also, because when you square it, it becomes positive. So that's where this portion comes from. And that one goes closer to y equals negative x. On the other hand, they could both be negative. So this is just the basic idea of why we might expect to get a shape like that. It's kind of like the letter x a little bit. Or it's like 2 parabolas that are going in opposite directions. So there are 2 asymptotes. Now you might say, that's kind of strange. Why, on the one hand, do we have like xy equals 1 makes a hyperbola looking thing, the product of 2 things. On the other hand, here we have the difference of 2 things makes the same shape. And that's weird, because one of them is a product and the other one was a difference. Well, not to make too much of a analysis of this, but unlike x squared plus y squared equals 1, where you can't like do anything with it, x squared minus y squared equals 1 can be factored to x minus 1 times x plus 1. Sorry, x minus y times x plus y equals 1. And the idea is, as x minus y gets, as x, I'm going to write it x plus y, x minus y, switch it around. as x plus y gets bigger, x minus y has to get smaller to compensate for it. On the other hand, when x plus y is 0, then there's no number that can cause the product to become 1. But x plus y equals 0 can't happen, and that's kind of like the asymptote y equals negative x. And over here, x minus y, if that were ever 0, we couldn't get any points because the product can never equal 1. And that corresponds to this. So it's kind of, in that way, there is a relationship between like xy equals 1 versus x squared. Like they're not totally different things, even though at a first glance they might seem to be. Now, we can do some transformations of x squared plus y, x squared minus y squared equals 1. Namely, if I put denominators in, we get like a distortion of this, kind of like the way an ellipse. And this looks like an ellipse equation, except there's a minus instead of a plus. So just like an ellipse is a distorted circle, a hyperbola is going to be some sort of distortion of this, like most basic hyperbola. And here's the way it works. First of all, a hyperbola has a center. And in this case, the center is 0, 0, because it wouldn't be 0, 0 if there was like x minus h and y minus k. But in this case, it's 0, 0 is the center. Now, if you plug y equals 0 in, you would get x squared over 4 equals 1, x squared equals 4, x squared equals plus or minus 2. And those would be the x-intercepts. And in general, if we rewrite this 4 as 2 squared, those are the x-intercepts. Now, if you try to get y-intercepts, something strange would happen. X equals 0, you would get negative y squared over 9 equals 1, y squared equals negative 9, and you get imaginary numbers. So that doesn't seem that useful for graphing. However, there is going to be like a sneaky trick that I want to show you. To graph a hyperbola that's in this form, I'm going to, if you don't mind, I'm going to write these both. I'm going to write this as x squared over 2 squared and y squared over 3 squared. In this case, the number underneath the x is kind of like a squared, and the number underneath the y is kind of like b squared. So this thing looks like an ellipse, and the trick for making the graph is to start almost like you're making an ellipse. So you go left and right 2 units, because the 2 squared is underneath the x squared. And then you go up and down 3 units, because the 3 is underneath the y squared. Well, you might say, didn't I just say there are no y-intercepts? That's true. Those 2 points that I just drew, those y-intercept points, aren't actually on the hyperbola, but they're going to help us draw it. Now, here's the way we draw it. Instead of joining these 4 points to make an ellipse, I want you to make vertical and horizontal line segments to produce this rectangle thing, this dotted line rectangle. Then, as a dotted line, you make the diagonals of that rectangle. So I have these 6 dotted lines, the 4 sides of the rectangle and 2 diagonals. So what do you think those 2 diagonal lines are? And they are the asymptotes. Now, these 2 points are the vertices. And these other 2 points are actually, we don't use them at all. So what you do is you draw the branches of the hyperbola, make sure you make them like get closer to the asymptotes as they. Okay, and that's how you draw sketch of the hyperbola. So it's x squared over a squared minus y squared over b squared equals 1. The a and b get you these 4 points that form the box, although only 2 of the points get used in the hyperbola. The other 2 were just used for creating that rectangle. I would want to say a little bit more, which is this. The reason that those asymptotes are the diagonals of the box, one way to think of it is if I factored, I think, x over a minus y over b times x over a plus y over b equals 1. So when any of these equals 0, like in this one, if I said, well, that can't equal 0 because otherwise the product of 0 and anything is never going to equal 1. And we end up with x equals a over b. Actually, I'd rather write y equals b over ax. And b over a that's the equation for the asymptote, y equals b over ax. And this other asymptote is y equals negative b over ax. So these two asymptotes are not perpendicular, but they're just negation. Their slopes are negatives of each other. That's kind of where that comes from. So we have the slope of the asymptotes, or the equation of the asymptotes. Now, there's a question on the Desmos activity. Where they want you to do practice one. So you can take a minute to do that. Okay, now hyperbolas don't have to be centered at 0, 0. So you could have something like x minus 2 squared over, let's just say 5 squared, minus y plus 3 squared over 2 squared equals 1. And that's the same idea, except the center now is 2 comma negative 3. So we graph that first. Then we go 5 to the left, 5 to the right. Those are going to be our vertices. Then we go 2 up and 2 down. Those are not vertices. Those are just those are points that help us draw the rectangle and the diagonals of the rectangle. And then from the 2 vertices, we can draw the branches of the hyperbola. In the Desmos activity, actually, I have these links also. Not that, but these. So there's links in the Google Classroom where you can drag around the, not that one, sorry, but this one. It says Hyperbola Horizontal. I'll talk about the other one after. So you can mess around with dragging the, changing the size of the box and moving the center around. Here's the equation, x minus h squared over a squared minus y minus k squared over b squared. So you can mess around with that. And then on the Desmos activity, you can do this question. Oh, sorry, not that one, but this one, where you where the hyperbola is shifted. Now, there's 2 other types of hyperbolas I want you to be aware of. Sometimes the equation looks like this: negative x squared plus y squared equals 1, or it could be written as y squared minus x squared equals 1. So what we have here is the y is the positive thing and the x is the negative thing. And when that happens, we still end up, like in this case, if I put it over 1, I personally like this way of doing it. We still make the same box and the same diagonals. But in this case, the thing underneath the x squared is known as b squared, and the thing underneath the y squared is a squared. And in this case, the big difference is, see, if I try to get y equals 0 on this one, I would get negative x squared equals 1, and I would get imaginary. So this one doesn't have x-intercepts. Instead, if you let x equal 0, you get y squared equals 1, y equals plus or minus 1. So the difference is that the 2 points that are the vertices are no longer sort of the left and right points, but the up and down points. And our hyperbola is going to be an up-down hyperbola. So another example would be negative x squared over 4. Actually, why don't I use the same examples here? Oh, yeah, I am. Minus y squared or plus y squared over 9. So for this one, even though this thing officially is b squared now, and this is a squared, we still go, it's whatever's underneath the x squared is how you go left and right. And whatever, the square root of whatever's underneath the y squared is the up-down thing. And you make exactly the same rectangle and exactly the same asymptotes. The only difference is these two things become the vertices that give us the branches. So would you go over to the Desmos activity and go ahead and do, not that, sorry. Do this. This question, sorry. Minus x squared over 25 plus y squared over 9 equals 1. So take a minute to do that kind. Now we can also have shifted versions of that. So if I have x plus minus x plus 3 squared over, I'll just say over 4 plus y minus 1 squared over 25 equals 1. Well, again, this time the center, sorry, the center now is at negative 3, comma 1. You draw the center, even though it's not officially part of the hyperbola. Then we go left 2, right 2 to make the box. We go up 5, down 5. We make the box. We make the diagonals of the box. Then the big decision is which two things are the vertices and which are not. Well, the top and bottom of the box are the vertices in this type. And that's what it looks like. You could actually go over to this diagram and you can move around. You see I have the equation negative x minus h squared over b squared plus y minus k squared over a squared equals 1. And you can drag all these 3 points around to watch the way that changes. And then you can go over to the Desmos activity, and you can do not this one. I'm going to rearrange these for you guys. This one, negative parentheses x minus 2 squared over 16 plus y plus 1 squared over 25 equals 1. Now, in the up-down type hyperbola, the asymptotes now are, this is a little confusing because in the first one, the asymptotes were b over a. But in this one, the asymptotes are the slope is a over b. And that is a bit confusing. You might say, oh, how am I going to memorize, or how am I going to not get those things backwards? Well, you don't have to think of it as b over a in the first case and a over b in the second case. you could just, so in this case, it's y equals 5 over 2x and y equals negative 5 over 2x. You don't have to really think of it in that way. I personally don't really think of these numbers with a's and b's. The asymptotes are always the square root of whatever's underneath the y squared over the square root of whatever's underneath the x squared, whether you're calling it a and b or not. But I mean, officially, the thing with the plus sign is the a squared, and the thing with the minus sign is the b squared. So for this type of hyperbola, it's going to be a over b is the slope of the asymptote, not b over a. But in both cases, the thing underneath the y, the square root of that, will be in the numerator. And the square root of whatever's underneath the x will be the denominator. That's true for the up-down hyperbolas. And it's also true for the, where is it? For the side to side. So over here, for instance, it's 5 over 2, again, even though that's officially b over a, but it's still whatever the square root of whatever's underneath the y squared over the square root of whatever's underneath the x squared. Now, there are some delta math questions for you to do. You can do there's 4 delta math questions for you to identify the equation, one for a left-right hyperbola with center 0, 0, one for left-right with a shift, one for up-down with center 0, 0, and one for up-down with a shift. Okay, another question I want you to be aware of is one where you're given a graph of a hyperbola. You're told the center, and you can see what the 2 vertices are. And we're not given the that box, you know, that the whole box that helps you see what the other denominator is, but we are given the equations of the asymptotes. So what we can do, we have some decisions to make. First of all, it's x minus 2 squared, and it's y minus 3 squared because the center is not at 0, 0 equals 1. So we have that. That's just based on the center point. Now we have to make a decision as to whether to put a plus here and a minus there, or should it be a minus here and a plus here? Okay, which do you think it is? And in this case, it's plus here and minus here, because the left-right hyperbola is plus x squared minus x squared, whereas the up-down ones are minus x squared and plus y squared. So that's a decision that sometimes people get like backwards. And now, well, even though we don't see the box, we can see that it would be left and right 2. So underneath the x squared, we'll put the 2 squared. And now we can take the slope, which is 3 over 2, and that should equal, by the way, underneath here, I'm going to write b squared. So the 3 over 2 should be whatever's square root of whatever's underneath the y squared, which is b, not to be confused with y equals mx plus b, over a, which a happens to be 2. So we solve for b, which is 3 in this case, and our answer is that. So that's another question you could do. There's going to be 2 delta math homework or classwork questions for you to do. Okay, well, that's what I wanted to show you today about hyperbolas and graphing them. You can, mess around with moving. It's fun to move these around. You could actually also control them with these sliders. See the equation over there. And we've learned how to graph them and how to, we've learned how to graph hyperbolas, the 2 different types. We got a little insight into why the graphs are what they are, and saw that you can find the equation. If you have the picture of the entire box, that's easiest. But if you have just the asymptote, you could also work out the equation. Okay, that's going to be good for today. I hope you learned how to do this.